Thank you everyone for joining us today, day one of reInvent 2022. My name is Saikat Banerjee and I'm a senior database specialist solutions architect. I work with customers to migrate and modernize their database architecture to AWS managed database platforms. With me today, I have Kumar Bangalore, who is a senior director of database engineering from S&P Global. So today we'll talk about how S&P Dow Jones Indices modernize their environments with Amazon Aurora. So we'll get an overview of S&P Dow Jones Indices, a business overview, what they do. Many of you already know about them. And then their application landscape, what type of applications they modernized, migrated. And they took a phased approach, like rehost, replatform. How did they decide the rehost, replatform applications and what steps they took? What are the challenges? Then I'll talk about Amazon Aurora Overview, which is a cloud-native relational databases. I'll cover some of the key concepts and basic architecture. Then Kumar will go over what features they used from Amazon Aurora to modernize their relational database landscape and ultimately achieve efficiency through automation and cloud-native capabilities. With that, I'll invite Kumar to talk about S&P Dow Jones business overview. Thanks.
Thank you, Saikat. Good afternoon, everyone. I'm proud to be part of the index technology team at S&P Dow Jones Indices. S&P Dow Jones Indices is a business segment of S&P Global. When you watch CNBC or Bloomberg, you will notice on the bottom right-hand corner of the screen, our iconic benchmark indices, such as the S&P 500 and the Dow Jones Industrials Average. You see the ticker going up and down, right? So those numbers are calculated by our systems in real time and fed to the markets worldwide. We are primarily involved in calculating indices and feeding the data to financial markets around the world. We set industry standard across various asset classes. If you are looking at the slide, you will see we are the world leaders in several global benchmarking indices. Financial investors, investment services around the world use our real-time market performance and also use the index data as input to some of their financial decisions. Our clients include BlackRock, Invesco, State Street, Vanguard, and many other investment services companies. We also provide historical data around these indices since the beginning of the creation of these indices. So if you want to go back in history and look at S&P 500, what it closed 40 years ago, and what were the stocks in the 500 at that time and their closing prices, you'll be able to find those details. Recently, we have been focusing on building some newer indices, thematic indices focused on economic, social, and governance factors, right? And our new economy indices also look at some of the industries like robotics, artificial intelligence, nanotechnology, genetics engineering, and various types of industries that are going through transformation. Late last year, we launched the S&P 500 Twitter Sentiment Index, basically which captures sentiments around financial tweets and uses that as a score, aggregates the score throughout the day, and then calculates the index based on the sentimental score of a given stock on a given day. Unlike the traditional way of using equity prices to calculate an index. Let's take a look at the applications that perform these calculations. Our core index services platform ingests several millions of stock indices at stock prices at the end of the day and calculates nearly 1 million indices, including the global benchmark indices. This platform also performs rebalancing operations around these indices as well. Our next platform is our fixed income platform, creates nearly around 3,000 plus bond indices over various types of bonds, corporate bonds, municipal bonds, sovereign bonds, inflation bonds, and bank bills, many other types of indices. The next platform is our derivatives platform, what I call the derivatives platform. It's basically strategies on option equities and commodities on indices. We also have a platform that calculates indices for commodities. Our index data services and web services platform basically provides index data for research, index comparisons against active benchmarks, and also our web services provides capabilities where you can look back on some of the historical data. The real-time index platform is the one that's feeding the S&P 500, Dow Jones Industrial Average, and many other real-time indices, 400, 600, many others. I mentioned about our ability to create custom indexes. For some clients, we create indexes based on the portfolios they provide, and we calculate the indexes to them. And I mentioned about the scoring platform, and recently we have been using machine learning models to classify various assets around the newer industries. Supporting these applications are nearly 200 databases of sizes ranging from 500 gig to 15 terabytes. As you have seen, most of our data is real-time, transactional, highly transactional, and a historical database going back into the history of the creation of these indices. And some of the data is also highly confidential data, especially around corporate actions. You all are familiar with the stock being added into the index at any point of time. Some stock is being removed, but the data is highly confidential up to the point it becomes public. We call it NPI, or non-public information. On the right-hand side, you see our data center infrastructure. We're spread across 3 data centers, New Jersey, Chicago, and London. And this is how our databases are. We have the Oracle database. The real-time index platform is a 2-node Oracle rack running across 3 regions. It uses Golden Gate for data replication, bidirectional data replication, and keeping the databases in sync. That's how we are able to provide real-time indexes to the markets around the world. The 4-node rack is the one which is our core index service platform, which calculates the end-of-day values of nearly 1 million indices. The derivatives platform is our MySQL platform, uses bin log replication across the 3 data centers. Our fixed income platform uses Oracle databases. Also, some of the bond instrumentation, there are nearly 3,000 financial parameters associated with the bond. So a relational database model would not be the right fit. So that's when we decided to use a NoSQL database like MongoDB. And we built the MongoDB infrastructure, 4 shards, 2 replica sets, spread across the 3 data centers. Now, you all know that database administration across these databases is a resource-consuming operation. We all know that there is 24/7 monitoring. You have to make sure you have your databases in sync across data centers, whether it's data guard or bin log replication or MongoDB replication, and also your day-to-day maintenance activities like backups, daily, incremental, weekly backups, weekly full, monthly for retention, long-term retention, and all that. There is so many maintenance activities, and there is the request from database developers, QA team members, and production support teams for various purposes. So you have to keep making backups, refresh them, or restore them into the corresponding environments and provide them those copies. These are all operationally time-consuming tasks. On top of it, when there is a need to build a new database server, you need servers, storage, network, so much from an infrastructure standpoint, right? So that's when we began our cloud journey and decided to utilize AWS with the lift and shift approach. We identified the comparable EC2 instance classes and sizes, used general purpose storage, and were able to build some of our servers, the web servers, the application servers, middleware, and file servers, all on comparable EC2 servers, the C class, M class, and R classes. We also built our database servers in the cloud on EC2 instances comparable to our physical servers. We exported, for Oracle 19c, we created it as a physical standby database in cloud using data guard, and at some point we did the switch over and cut over to the databases in cloud. Similarly, for MySQL, these databases were small size-wise, less than a terabyte. So we were able to use MySQL export and import into the database. For MongoDB, we had to build the entire infrastructure, the 4 shards with 2 replica sets spread across multiple regions in AWS. And then we did a MongoDB export and imported into the cloud. Once we were in the cloud, we were able to leverage the S3 storage for backups, RMAN with OSB, Oracle Secure Backup to back up the databases. We also built cross-region disaster recovery databases in other regions, used the same technology we used in on-prem. Database monitoring, we built our OMS servers on EC2 in cloud and started using Oracle Enterprise Manager for MySQL and Oracle. For MongoDB, we built the database, the block stores on S3 buckets. And then we also built the Ops Manager on EC2-based database instances. Now, that only cut down the time you needed to build a new database server in the cloud, but you still had to do the installation, configuration, and set up everything. So it didn't technically cut down the maintenance resource, right? That's when we started to look at Amazon RDS, or what they call AWS RDS, or it's more like Amazon RDS. Most of you may know the benefits of Amazon RDS, the ability that AWS manages the database service, especially at the infrastructure level, handling the business continuity, high availability, all that, and most of the database administration aspects are taken care by RDS, right? So you have the ability to create a database of any type, Oracle, MySQL, MSSQL, Postgres, within push of a few buttons. And then you are also able to use the multi-AZ capability where AWS transparently builds another instance in a different availability zone, and it will fail over when there is a crash and transparently provides high availability to customer applications. So that was the best thing we were able to utilize. On top of it, we were also able to create read replicas, both locally and cross-region for disaster recovery. And so we migrated some of our databases from EC2 to RDS. We did an export of the Oracle database into Oracle RDS. And same thing with MySQL, we exported and imported the databases. And once we were built on RDS, we created read replicas. And we were also able to utilize the snapshot capability that RDS comes with, which are daily snapshots for providing refresh copies to developers, QA teams, and production supports. We were able to copy the snapshots using our own Lambda functions and restore those databases as and when necessary. From a security standpoint, we continue to use RDS-level security groups, private subnets, and also use storage encryption at rest, and also used SSL for our application connectivity to the databases. We continued our automation capabilities on these RDS. We used CloudFormation templates and built all these scripts so that our developers, our production support teams, were able to create new instances at any given point of time with these scripts, which had all the standards. We also scripted the failover failback scripts, integrated them into Jenkins, and provided those scripts to our level 1, level 2 support teams. So anytime there was a region-level disaster, they had the ability to click off a button, switch over the databases to the other region. So that took care of several maintenance tasks that cut down our operations reasonably. But then there was always challenges around performance. Now, here is our hybrid infrastructure, how we were set up. You can see that we had to use the cloud, but we continued to use our on-prem data center because Oracle RAC is not supported in AWS. You all know that. With the use of FlashGrid, there was a possibility, but we continued to stay on Oracle RAC. So our real-time platforms and the core index services platform continue to stay on-prem. But the rest of the databases and our application stack, we were able to migrate to the cloud. As we continue to grow with innovation and enhanced service requirements from our application teams, there was constant demand to improve database performance. So we always used to look at newer technologies, and that's when we started to look at Aurora. Before I continue on Aurora, let me bring in Saikat to give an overview of the Aurora architecture. Saikat?
Thank you so much, Kumar. So how many of you are already using Amazon Aurora? Okay, so good amount of people. So you might be already know about these, but just to recap and set the stage. So Amazon Aurora is basically a cloud-native relational database that provides the simplicity and cost effectiveness of any open source database, but also the high availability and performance of any commercial databases. The best thing, like you can run any MySQL or Postgres database applications with minimal changes because it's web compatible on Amazon Aurora. And like many other services, it's also pay-as-you-go model. So let's take a look at the basic architecture and key capabilities, and then Kumar will talk us about how they leverage those capabilities. So Aurora topology primarily divided into two components, compute node and nodes and storage. So Aurora storage is basically spread across 3 different AZs. And it's a highly distributed, purpose-built log structure storage, very different than any other traditional storage. And for a simple architecture, for example, you have a read-write instance that's accessing the storage, distributed across 3 AZs, and your application can connect from different AZs to the same read-write instance. And the storage split logically into 10 GB, we call protection group, and it automatically grows up to 128 TB today. So how does it write? So when a write request comes, it writes only the log records. To the contrary of traditional databases where it also writes data pages and many other write operation, in Aurora, we do write only the log records, and we write 2 copies each AZ to total 6 copies, so that at the storage layer, the data always become highly available. And the write is durable when 4 out of 6 writes is successful. We call write quorum. And then the acknowledgement sent back to the database engine. Very similar for reads. Aurora storage is very intelligent. So if the data is not in the buffer cache or shared buffer, whichever you call as per the different engine terminology, it will go to the storage, and storage can tell, okay, this node has the latest block, and it can find you the block. Under rare occurrences, like whenever failover happens or any recovery happens, in that case, it does need to complete 3 out of 6 read quorum so that it can read the latest data. And the storage you are seeing here under the hood, basically, it's hundreds of storage nodes. We logically present that as single storage volume to the EC2 instances on which Aurora runs. But at the back end, it's basically hundreds of storage nodes supporting a single Aurora cluster. Now, in a distributed systems, failure can happen anytime. So for example, if there is a segment failure, how do we repair? We just do peer-to-peer gossip protocol from any other segments, preferably in the same AZ, but it doesn't need to be, and we repair online. So your application is not impacted at all. Same with if the entire storage node gets damaged or impaired, we just replace the storage node by, or recreate the storage node, and it also happens online. So even the entire AZ goes down, 4 out of 6 write quorum can still go through. And in case there is additional segment impaired, we can just repair and build it online so that it can tolerate AZ plus 1 failure. Now what about compute node failure? Unlike traditional databases, Aurora read replicas can act both for read scaling as well as failover target. So it does provide high availability as well as read scaling. And we do update the read replicas buffer cache by sending the changes asynchronously. And you don't need to basically have dedicated separate storage, apply recovery like traditional database technology. Rather, we are just updating in memory the log records. In that way, we can maintain very low replication lag. And you can do up to 15 read replicas in a single cluster to scale your reads. Now, what happens in case of the writer node instance fails, or maybe any hardware issue or AZ issue? It just fails over to the target read replica. And the endpoint read and writer endpoint remain same, the cluster endpoint, so your application doesn't need to make any changes. And you can decide which read replica you want to set as a target for failover by using something called failover tiering. So we learned about scaling read replicas or scaling reads in the same region in a single Aurora cluster. What about scaling reads cross-region? We do that by using Aurora Global Database. Aurora Global Database also provides very low RPO and RTO, disaster recovery mechanism. So it can maintain basically very low replication lag for cross-region replication, typically within less than a second, and you can promote or achieve an RTO within a minute from the database tier. So let's see how it works. So for example, you're replicating from region A to region B, and under the hood, we create basically replication infrastructure, which is fully managed service at the storage layer on the source side replication servers, on the target side replication agent, and the log records, when you push to the storage on the source side, we do replicate via replication servers, replication agent to the secondary regions or secondary clusters, and they do get applied to the secondary cluster storage. And you achieve your durability and achieve your DR goals or disaster recovery. So in this architecture, you are seeing on the region B, there is no read replica. So we call it headless implementation. So in case you don't need to have very low RTO, you can afford to add read replicas or instances during a disaster. You can just reduce your cost by running Aurora Global Database in a headless mode. But you can also create read replicas if you want to very low RTO, or you need read capabilities on the DR side. And the process is very similar. The log records get replicated and updates the cache or shared buffer. And you can have up to 16 read replicas in the secondary region, and you can have up to 5 regions, so total 90 read replicas to scale. So any log records changes come, they do get replicated by replication servers and via replication agents on the target side and get applied to the Aurora storage. So what happens if a region fails over, right? The entire region, although very rare, but still it can go down. You just promote region B with a simple API call, and it becomes a single isolated cluster. And on the application side, you just need to change the cluster endpoint for the new clusters. So in the previous slide, we saw how you can leverage Aurora Global Database for disaster recovery. Now let's say you have your customers or users at different regions. They need very low latency reads. You can use Aurora Global Database for local reads from different regions also. And you don't need to have same topology or architecture. As you see here, in the region B, you have 3 read replicas, region C, 2 read replicas, and region D, you may be just using for disaster recovery with headless or no read replica architecture. Now, there may be use cases when the remote region or applications running in a specific region, remote region, need to write also, not only read locally. So in a typical setup, application will try to write to your global database, but since it's read-only, the write should fail. So what you need to do in that case, you need to create tunneling so that you can write to the primary region. You need to manage 2 different endpoints. You need to set up networking setup. That's not a good experience, right? So in Aurora MySQL, there is a feature called write forwarding. With that, you can write locally to the remote region and write by using the parameter called enable write forwarding, and writes get committed to the primary region, and the data finally gets replicated back to the remote region where the write is issued from. Now you can tune and use some consistency parameters to ensure how stale the data you want to see. Do you want to see the latest data, or do you want to, you can afford some staleness in the data. So all those tuning are possible. But this basically helps you manage a single endpoint and perform occasional write, rather than setting up networking setup for a remote region or managing multiple endpoints from the application side. So we learned how to scale Aurora in the same region with multiple read replicas or vertical scaling, having a bigger instance. We learned scaling across regions. Let's talk about something different scaling method or mechanism in case you need to scale hundreds or thousands of transactions within fraction of seconds. Aurora Serverless V2 can do that with something called in-place scaling. So for example, you're running a flash scale events, you don't know how many users will be logging in or will be doing transactions. You can use Aurora Serverless V2, which supports both PostgreSQL and MySQL compatible editions to scale instantly with hundreds of and thousands of transactions. And with serverless, Aurora Serverless, we call it ACU, or Aurora Capacity Unit, which is basically one ACU is equivalent to 2 GB memory and corresponding compute unit. And while scaling, we'll scale granularly every 0.5 ACU. In that way, you basically use only the capacity you need to use and don't over-provision. And Aurora Serverless V2 comes with all key capabilities, like global database, read replica with multi-AZ deployment, and if you use it prudently, rather than using provisioned Aurora by provisioning for peak, you can save up to 90% cost for perfect workload. I mentioned about Aurora Storage. It's a very intelligent, very innovative storage solution that is supporting Aurora Service. Another feature that's from the storage layer is fast cloning. You might be always needing to quickly provision your dev test environments with the production data, or maybe like quickly provision an environment where you want to do some testing, deploy some codes, run some workload, or maybe run long-running queries from maybe some machine learning models. And you need to quickly provision an environment or cluster. Aurora fast cloning can let you do that. So for example, you need to run a reporting application. You just create an Aurora clone, which you can do cross-account as well, if you want to provision lower environments with the same data. And for multi-TB setup, you can provision within few minutes. How it does? It basically does not charge you duplicate for the storage. Rather, the storage in the clones point to the original storage in the primary cluster. So for example, the storage basically is a pointer to the original primary cluster storage. So for example, you have created a clone, you want to create some indexes, right? And so it updates changes the block. Then you do some DML, some write operations. It also updates the blocks, the storage layer. So whenever you do some different, maybe you update in the original cluster or update in the clone cluster, it diverges. So it's basically a point-in-time copy, and then it uses copy on write protocol. And the time it starts new transactions in the clone side, or maybe the source side, source cluster side, it diverges. So as you see, as we created new indexes or updated new rows, it diverged. What happens if we update the rows in the source cluster? Because the clone volume, the clone cluster still need to use the old blocks, right? So we basically take a pre-image, and clone cluster can use those old blocks. So these are the very key capabilities that you can leverage for your day-to-day operations, reduce operational burden. But observability is also a very important part. And with Aurora Platform, both MySQL and the Postgres, you get end-to-end observability. Like, for example, operating system level metrics like CPU, memory, or maybe read, write, IOPS, throughput, you all can measure from CloudWatch metrics. Also, you can export your database logs to CloudWatch for different use cases. Maybe for long-term retention, you want to run log analytics, you want to create CloudWatch events, depends on various database errors. So CloudWatch should be used as a leading indicator if there's some problem or not. But enhanced monitoring can help you dive deeper. And you can do basically per second granular monitoring. And with enhanced monitoring, you can list down all the operating system processes, how much CPU each of them are taking. Pretty much kind of top output you get in a Linux system. And there are performance insight that basically provides you database level wait events, top SQL statements, and various counters like how many rows updated, how many temp tables created, more of database level performance analytics. And we also have Amazon DevOps Guru for RDS that provides machine learning capable insight on wait events. Also, it detects anomalies on the performance and provide more granular, more detailed recommendation on various wait events. Also points to newly built documentation by the DevOps Guru team to easily troubleshoot various wait events related problems and other performance anomalies in Aurora platform. Also, Kumar talked about security was a big challenge in the on-prem world. Aurora provide end-to-end security from networking layer, like from security group, NACL, as well as putting the clusters in private subnets and choosing right VPCs, encryption at rest in transit using KMS or Key Management Service or TLS respectively. With IAM policies and roles, you can control who can launch your cluster, what operations they can perform on your clusters. You can go as granular as like instance class selections. And also various capabilities in the authentication and authorization aspects, right? Aurora supports IAM authentications, supports native password authentications, or also supports Active Directory or Kerberos authentications. Auditing is very important, especially in financial services in the industry like S&P Dow Jones. So you can audit across different layers from VPC or networking layer using VPC flow logs. Database activity stream basically streams all the database changes in a Kinesis stream. You can restrict who can access those Kinesis stream. That's how we can basically create another layer if you want to protect the audit records from DBA or group of people by controlling access to the Kinesis activity stream. And there are Amazon CloudWatch logs also, which basically you can always run log analytics on top of that. Now I talked about Amazon Aurora key capabilities and monitoring security. But how to migrate to Amazon Aurora, right? Primarily, the migration process are two types of migrations. Either you're migrating homogeneous, either MySQL or Postgres compatible sources, or heterogeneous, like you're coming from SQL Server or Oracle. For homogeneous process, typically the native method performs well. For example, Aurora MySQL. For MySQL source, you can take a Percona extra backup, restore it to Aurora cluster, and changes can be replicated via bin log replication. Maybe for Postgres, you can take PG dump, restore it, and set up PG logical replication for near zero downtime migration. But what about heterogeneous migration, like Oracle to Postgres? So tools like database migration services and schema conversion tool helps you there. Schema conversion tool is a standalone tool. You can download it from AWS website and install it on your laptop or EC2 instance. It helps you convert your schema from heterogeneous source to another target, for example, Oracle to Postgres or MySQL to, or maybe SQL Server to MySQL, etc. And not only does convert the objects, it also converts the stored procedure or code components, also even embedded in the application code, right? Embedded SQL statements in Python or Java. Once you convert the schema, then you can migrate the data using AWS DMS. And both the tools support different combinations of source and targets. Even DMS supports many NoSQL targets. So I'll recommend to take a look at our public documentation, official documentation, to see the current supported version, the target and source. So with that, I'll invite Kumar to share his experience about migrating to Aurora platform.
Thank you, Saket. That was quite a detailed overview on Aurora architecture, the features and capabilities. Once we realized that, we decided to migrate some of our MySQL databases to Aurora. And our derivatives platform, the Indices platform, we decided to migrate from EC2 to Aurora. It was a small database, so we were able to utilize MySQL export and then import it on once the Aurora database was built. We built an Aurora global database. Right around that time was a need to build the scoring database. Remember I mentioned about the sentimental scores that we capture from financial tweets and aggregate that to create a score around an equity to build the sentiment index. So when we built the score platform, we wanted to make sure that we are able to ingest the Twitter feeds in all regions. So we wanted to create the database active in all regions. So we built the database, MySQL RDS, and then we leveraged DMS CDC, continuous data capture for bidirectional replication. We also built some of our newer thematic indices, especially around new economies on Aurora global databases. These databases also use the ability to do, we enabled write forwarding so that we could also keep the databases active in both regions. Applications could connect to the database in any region and still be active to perform some of the application functionalities. Our demand for index data services and web services increased, so the database performance was at most a critical need for us. At that point, we decided to migrate some of our databases from Oracle to Postgres. With that, I captured this slide from the AWS playbook, particularly around schema conversion, right? Saikat already told us about the schema conversion tool and the DMS for database migration. But what was the important one was this, what they call the SCT action code index. It has two major factors. One is about the compatibility at the database level, right? Your schemas, the tables, the different data types that are used. And then the next one is the automation of your code, the automation level. So they call the automation legend. So somewhere when you evaluate your database, you need to highlight what level the compatibility is at the database level and also at the automation level. We picked some of our Oracle databases which had the highest compatibility and the highest automation. And then we were able to perform the schema conversion and then also do the database migration and move them from Oracle to Postgres Aurora. But our index data services platform, which holds our historical database, which is almost 15 terabytes, when we looked at the evaluation, we found it somewhere between medium high on the compatibility and same thing between the automation level, between medium and high. So when we went through the schema conversion, we had several challenges. And I'm highlighting some of these challenges that we worked through and solved them. AWS IEM team, they call Infrastructure Event Management team, was able to help us out providing some guidance around these schema conversions. One main thing is, in Oracle, when you have numbered data types, when you pass it through the schema conversion, it gets converted to numeric. The problem with numeric is it takes 256 bytes, and if that field is used for joins in your SQLs SQLs will be slow. So we had to manually tweak some of them to int or big int, depending on whether it's a 4-byte or 8-byte, depending on whether it was a floating point, however we needed in our application. We had a lot of partition tables, 15 terabyte database, some tables, single tables larger than a terabyte. And some of the tables, partition tables, list partition tables, we had thousands of list partitions. And composite partitions with range hash, range list, many other partitioning demands. So we had to make sure that all those went through the conversion. One thing we found out is that the list tables, the DDL that got generated out of the SCT did not match the DDL on Postgres. So we had to manually tweak some of the list partition DDLs to create them in Postgres. And with the stored procedures, packages, and some of the functions, we had to recode them to ensure that the PLPG SQL was compatible with the PLSQL functions, right? You know that in Oracle, there is a password verify function where you can build your own custom rules adhering to your corporate standards. So when we looked at that capability, that does not exist in Postgres. So, well, we had to use other solutions like AWS Secret Manager and many other SSM storage parameters to accommodate for the password rules. That was missing in Postgres and nothing to do with schema conversion. But at least for some of the data which had to go through the encryption, in Oracle, we were using DBMS crypto to keep the data encrypted. So we were able to use PG crypto in lieu of DBMS crypto for some of those conversions. Performance regression with prepared statements. Now, this is a critical one. You know that if you have a prepared statement and if you run multiple statements which are similar in a single session, you get great performance benefits. Unfortunately, that was not the case because most of our SQLs use bind variables, especially with historical data. Customers can pick any range of time when they're looking at data that they want to pull from our website. So because of passing the bind variables, we could not leverage and use some of the performance, the prepared statements. And you know that Postgres does not allow transaction control inside PLPG SQL. What does that mean? A unit of work, you know, when you have the begin work and the commit work, ends the work, and at that point, when you start, in Postgres, what happens, the next unit of work starts right after the last commit. Whereas in Oracle, a unit of work does not start until a DML is issued. Okay? So there are subtle differences when it comes to handling transaction control. You have to be very careful and evaluate your application logic and your data sanity logic that it's being taken care of. Same thing with runtime exception handling. Your exception handling transactions in Postgres are treated as sub-transactions. So in sub-transaction, it can fail by itself, and you don't have to roll back. Whereas in Oracle, if your exception handling fails, your entire transaction rolls back. So you have to be careful how you are coding. It is a benefit, but at the same time, you have to make sure your application logic is good and will conform to what your functions are, right? So we went through some of these schema conversions for our large database. Then we started the database migration and 15 terabyte database from Oracle to Postgres, Aurora Global Database. We created a second standby database and used that as an Oracle source database to our Postgres target. When we created one DMS instance and performed the task migration serially, it took more than 36 hours to do the 15 terabyte migration. We couldn't afford to have that type of a downtime. So what we did, we built 3 DMS instances, and then we also split the task and mapped the task for each one of the instances. We also created the task using API. We scripted that so that we could launch all the tasks in parallel to have parallel tasks going across the 3 DMS replication instances. We still had DMS challenges. Database migration is not an easy thing for a 15 terabyte database. So when the AWS IEM team looked at it, what they noticed is right at that time, there was a newer version of DMS that had got released with more capabilities. So we were able to upgrade the DMS class across all the instances. Another thing is our target Postgres Aurora global database. We created it as a global database because that's what we wanted. We had a primary writer with 2 readers on the primary cluster. We had 2 readers in the secondary cluster. So when we initiated the DMS, the WAN traffic was significant between the primary cluster and the secondary cluster cross-region. So we were recommended to drop the secondary cluster and also drop the local readers and keep it to just one single writer to reduce the WAN traffic. Another thing we observed is that I know that within zones, there shouldn't be an impact in performance, but we did see subtle differences with respect to the traffic. So we created the DMS instances, the source Oracle database where it was, and the Postgres, all within the same availability zone. Couple of recommendations we got was also to upgrade one of the DMS replication to R6i. Our instances are already memory optimized, but the R6i with 64 CPUs and 512 gig memory was able to provide us with many more capabilities in terms of database migration, particularly for large tables, which were more than a terabyte each. We also noticed for some of the partition tables, the network bandwidth needed was significantly high. So we were given recommendations to use a C class for one of the DMS instances. By default, when you start your Aurora Postgres database, auto vacuum is enabled. But that brings in a lot of process overhead when you're doing the database migration. So we had to defer. We were given the recommendation to defer the auto vacuum. And also the connection parameters, some of the endpoint connection attributes, and also some of the connection attributes in the database itself. This was able to increase the transfer throughput, particularly with large data blocks, with blob types, where your single row would be a very large size. It is better to see that there is less network overhead by utilizing some of these connection parameters. With all these changes, we were able to cut down our migration time to less than 10 hours. So it was a great journey. So once we were done with the database migration, we ended up with our standard database architecture with the primary database with writer and 2 readers locally. Application teams were also able to leverage using the readers for doing their reads, especially for the historical and the web services requirements. And we also were ready for disaster recovery with 2 readers on the secondary cluster. So we ended up with this architecture. Once we were on Aurora, RDS, and many other capabilities, we wanted to utilize some of the AWS services and increase our automation and achieve more efficiency, right? So the first thing we did, we built most of our provisioning scripts for RDS and Aurora databases of all the types, right? Oracle RDS, MySQL, Postgres. We were able to script them using CloudFormation templates. We were able to script the failover, failback capabilities and hand over these procedures to our production support, level 1, level 2 support teams to be able to perform these operations anytime they wanted. AWS backup. This is a managed backup service provided by AWS. It's a policy-based service. If you don't know, please, I would recommend to take a look at it. The ability that all you have to do is to create a backup plan with frequency of your backups and retention policy for your backups. And AWS will automatically copy the backups into a database vault and keeps them according to your retention. You can even set deletion protection on these backups with whatever time frame, and no accounts will be able to delete those backups forever. So there are many advantages with the backup services. The advantage we got is also the database refreshes that the development team, the QA team need for load testing, regression testing, and the production support team for problem management, troubleshooting, and root cause analysis. They were able to, with a click of button, be able to get a copy of the backups restored with shorter period of times. Database activity stream. I would recommend, I don't know if there is a session over this week, but I sincerely recommend this session. The service with database activity is that it captures all the audit logs across all the databases, RDS and Aurora, and streams it to a Kinesis data stream. Once it's in Kinesis data stream, we built our own Lambda functions. That's to exclude noise and include what is necessary, the critical data. And then we were able to ingest it into an OpenSearch bucket and then use the Kibana URL to build our own reports, audit reports for governance and compliance needs. User administration across 200 databases with almost 50 to 100 user accounts, schema accounts, application accounts, privileged access accounts, and named support user accounts is quite a bit of a user administration task. So we use SailPoint's identity management for the user administration. So that alleviated a lot of our resource requirements for database user account administration. For break-glass, especially for non-production support team members to connect to the production databases with the checkout, check-in policies, we were able to leverage and use CyberArk through their privileged access management to perform our break-glass actions. from a monitoring purposes. So we were able to use Datadog dashboards. We built a single pane showing all our databases, the up-down status and the various health checks. And we also were able to leverage using CloudWatch logs, build the proper alerts, thresholds, and also used AWS SNS for notifications. We also made sure to enable performance insights on our RDS and Aurora databases, because performance insights provides very detailed overview about performance issues and problems related to your database. And we made sure to enable auto miner version upgrade, and you specify that with the RDS. That's the other advantage you get, right? You pick a maintenance window, and then AWS service will automatically make sure to upgrade, whether it's a PSU level auto miner version upgrade, or whether it's a one-off patching upgrade, depending on the database type. System updates at the OS level to handle security vulnerabilities that are assigned periodically. That comes up as a pending maintenance on the status of your RDS databases. So if you look at the status when it shows pending maintenance, that means it's ready for an OS level critical vulnerability update. Once you provide the maintenance window, it does go through during that maintenance window. Database refreshes became much more easy because we were able to then use AWS backups and be able to provide copies to developers, the QA teams, and production support teams. With all these activities, we were able to increase our efficiency of operation, our quality of service, and also the speed and performance of many of our databases, and also be able to cut down our operational cost significantly. So this is how, in summary, our journey is. We did the lift and shift in the beginning, where we migrated our infrastructure from on-prem into cloud, used as a platform as a service. And then we moved to Replatform, or use some of the RDS or managed service capabilities in the RDS and Aurora. And finally, we modernized our applications using some of the capabilities. Once we were on Aurora, we also started to look at some of the other capabilities like EMR and DynamoDB for some of our applications. Also continued to use serverless for some of our newer applications. We recently went live with a serverless application, which had significantly a dynamic workload, so and so, right? So we were able to leverage the capability that you can scale based on compute units, particularly around our machine learning applications, which have the ability to ingest large amounts of data, do the processing to classify the assets across various industries, and then deliver those applications. So this was our beginning to end journey to the cloud. But this is just a new beginning. We are going to continue to use many of AWS components. With that, I want to thank the Index infrastructure team for helping us, and my database engineering team, who have continued throughout this migration journey and continuing to provide support. The Index technology team, consisting of the application teams, the QA teams, and our production support team, who have been very helpful. And the AWS IEM team, they are specialists in database migrations, so they were able to provide us with tips and techniques that are needed when you have to perform the migration. Last but not least, Datawhale DB Inc. Support team, they provide the 24/7 database support for us. I want to thank their team as well for supporting us. Thank you. Thank you.
Thank you, Kumar. So today we learned about key capabilities in Amazon Aurora, how large financial services or organization like S&P Dow Jones, they used migration path like rehost, replatform, modernization. It's important to choose the right path depending on your applications. Maybe they can go in parallel, just like you don't need to do first migration, then modernization. Depending on application, you can choose the right path. And also learn some of the key best practices for DMS and SCT conversion. Hopefully that will be helpful to make you successful in your migration journey. right? So this is not the end. There are many exciting sessions for rest of the week. I'll strongly recommend to attend the keynote by our VP of Database Analytics and Machine Learning, Swami Siva Subramanian, and database leadership session by our VP of Relational Databases and Migration, Jeff Carter. They're tomorrow. And thank you again for joining us today. Please provide your feedback by submitting the survey. And we are available for any question after the session, so please feel free to reach out to us. Thank you.